our 1.4 practice about dividing radicals. I hope you feel after a bit of practice that this skill isn't too heavy when it comes to the different types of things we might be asked to do with radicals. Although it may seem a little funky at the start, by the time we get into it a bit, there's really only so many tricks we could really be asked to resolve. All right, so the rule is if you see a radical on the top of a fraction and a radical on the bottom and they have some factor in common, you can divide them both just like you would be, say, simplifying a fraction. Really, it's exactly the same process. All right, so I would look at 12 and 6 and ask, well, what is the biggest number that goes into 12 that also goes into 6? And maybe you can see the smallest number. The largest number. But maybe you can't. And now, it's okay not to see the largest number right away. So what you could do is you could say, for instance, maybe, I can divide them both by 2. Because you can see that 2 goes into both of them. Okay, that's fine. And so you just go ahead and you divide 12 by 2, and you get, so you say it's root 6 over root 6 divided by 2 is 3. And that is simpler, but in this case, we can go a step further. So what we did is we divided by 2, and we divided by 2, and then we can say, 3 can also be multiplied into 6 and 3. So it's a common factor. So now we're going to divide by 3. We'll divide them both by 3. And that gives us root 2 on the top, because 6 divided by 3 is 2. And, well, root 1 on the bottom. And root 1 is just 1, right? So it's the same thing as root 2 over 1, which is really the same thing as root 2, which is the simplest form of that fraction. Now, alternatively, you might have noticed that actually the larger number that divides into 12 and 6 is 6, the largest common factor. And so you could actually divide them both by 6. Then you divide the top by 6, you get 12 divided by 6, which is root 2. And on the bottom, you get root 6 divided by 6, which is root 1. So at that stage, we simplify again just by writing root 1 as, well, just 1, and that just simply becomes root 2. Okay. So the point there is that it doesn't really matter if you saw the greatest factor of both of them. So don't get hung up on that. Just if you can see any factor that you can divide them both into, try to find the biggest one if you can, but if you're not sure, just take any number you know for sure goes into both and start dividing. And it's easier to see remaining factors once the numbers get a little smaller. Now, with these two, you can see that 25 goes into both of them. So we can divide them both by 25. So we're going to divide by 25, and we'll divide by 25. Now, when I say we're dividing by 25, we're actually dividing by root 25. This is just shorthand, because I'm really only looking at dividing 100 by 25 and 25 by 25. Okay, so that gives us, so it turns out there's 4 quarters in a dollar, right? So there's 4 25s in 100, so it leaves us with root 4. And on the bottom we get root 1, which we saw just becomes 1, which we eventually don't write. I'm going to write it for this one. Now, root 4 also can be resolved. So that could actually be rewritten as, well, it's just 2 over 1. And now might be a good time to write all my perfect squares down on the left margin of the page. 49, 64, 81, 100, 121, 144. And over here I'm going to write my perfect cubes because I've got some cubes here. So 1, 3 cubed is 8. No, 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. All right. Now, I haven't finished, of course. That actually simplifies. 2 over 1 is really just the same thing as 2. So, root 100 over root 25 was just a crazy way to say 2. And I hope you agree that that is simpler, objectively. All right. So here we've got some cube roots. Now it doesn't really matter what the index is. If the index was 2 here, the index is 3, but the rule is the same. We're just going to see if we can find a number that goes into 225, and we'll divide them both by it. Now if they end in 0s and 5s, you know they can be divided by 5, but you can see 200 actually is just a multiple of 25 itself, and so we can actually divide them both by 25. And so on the top, we're going to get the cube root of, well, if you have 8 quarters, you have $2, right? So cube root of 8 on the top, and cube root of 1 on the bottom. Now both of these are perfect cubes. They can both be resolved, so it's going to make it 2 over 1, which again gives us the answer 2. Okay, now the rule here is that we're really only looking at the radicals. We're not really looking at the coefficients. Coefficients may be simplified themselves, and they communicate with themselves. So this root 7 doesn't communicate with the 6, it only communicates with the 28, and to denote that, I'm going to highlight these two. All right, so whatever my answer is going to be, there's still going to be a 6 on the top, because it's not changing. Nothing to communicate with. Okay, now I ask myself what can go into 28, that also goes into 7, and you might see that they can both be divided by 7, and so that leaves us with root 28 divided by 7 is 4, and 7 divided by 7 is 1. And these are both perfect squares, 1 and 4, so I can simplify both of those. And it really becomes 6 times 2 on the top over 1, which is 12. Okay. Now, we'll take a look at this question down here, question E. So again, we're just looking for numbers that go into both. I can see that there's a 3 that multiplies into both negative 9, and 3. So I can divide them both by 3 to start. Divide by 3, divide by 3. And when I do that, I'm going to get 5 cube root of negative 3 on the top, and I get cube root of 1 on the bottom. Now, obviously, cube root 1 can be resolved because 1 is a perfect cube, but negative 3 is not a perfect cube. And so, that's interesting. I can write my negative perfect cubes up here. Right? They're all the same. Dot, dot, dot. Just negative. All right, so that means we've got 5 cube root of negative 3. Now, do you do anything with the negative value? Technically, you know what? I'm going to say I don't really care so much about that. Now, technically, you might say you could bring that negative out, but I really do think we're getting into that stage of like, well, what is simpler anyhow? So I'm going to say we can just leave it there when it comes to negatives inside radicals. Unless, of course, the index is even, in which case it's there's no solution. All right. Or I should say, rather, no real solution. It would be a complex solution. Okay, so here we have both a radicand on the top and the bottom, and they're going to communicate with themselves. And we've got these coefficients as well. They're green. Okay, I feel like that green's a little dark, so I won't use that next time. I'll try to use pink because it's a little hard to see it on the screen. All right, so we're going to ask what goes into 2 and 4. Well, the answer is 2, so we're going to divide both of those guys by 2. And so over here, all right, answer, so that's going to be 4 divided by 2 is 2, and 2 divided by 2 is 1. Okay. Now, for the radicals, I can see there's a number that goes into 18 and 3, and that's the number 3. So I can divide them both by 3. And so I'm going to get over here, I'm going to get a square root of 18 divided by 3, which is 6. And on the bottom, 3 divided by 3 is is 1, right? So this is square root 1. Okay. Now overall that becomes 1 square root 1, that's 1 times 1, so the whole denominator is 1. So the whole answer just becomes 2 root 6. Now I might stop and ask myself, is there some perfect square that maybe is a factor of 6? Because maybe I could simplify that further. But there isn't. Have a good night. So we're going to leave it there. That's fully simplified. Okay, so same thing here. We got some radicals. So we're just going to think about those separately. And the coefficients. There we go, pink. Yeah, I feel like, there we go. Okay, so what we're going to do here, same thing. Really, if you could do F, you could do G. We're really looking for two numbers that divide into 3 and 12, which is 3. And two numbers that divide into 32 and 8. Now, 8 is a factor of 32, so we can divide them both by 8. All right, so then we're going to get, well, we're going to get 1 on the top, and we're going to get 4 on the bottom. And then we'll get root 4 on the top, and we're going to get root 1. I'm kind of sick of writing root 1 on the bottom and then just simplifying it, so I'm actually not going to write it this time. Okay, and that just leaves us with 1 times root 4. And we know root 4 is a perfect square, so it can be resolved. That means the square root of 4, that's going to be 2 over 4. And that's all good, except actually that fraction can be simplified. We can rewrite that as 1/2 by dividing the top by 2 and the bottom by 2. All right. So next, we're going to kind of do the same thing. Again, it's a very similar question to this one. It just has different indexes, but really there's no other tricks here. Just some extra practice. So I'm going to highlight them like that to help me focus on which things communicate with which things. And I'm going to divide the top by, well, it looks like 48 and 8. 8 is a factor of both of them, and 25 and 5, well, we know 5 goes into both. Okay, so on the bottom, we're going to get 6 negative. And we'll get 6 on the top and 1 on the bottom. And over here, we're going to get cube root 5, and then cube root 1. Right, so 1 cube root 1, well, cube root of 1 is 1, so that all evaluates to 1, so we actually don't need to write it. So the answer is actually just negative 6 cube root 5. Okay. Now, well, pretty similar question to question G, I would say. We'll highlight them up as we normally do. So I'm going to kind of speed this up. If you really don't understand what happened, I'd like you to scrub back to G, because that just slows down, but it's really the same process with different numbers. 7 goes into both of these, so I'll divide that one by 7, and that one by 7. We'll get 3 there, and these ones, I can see 7 goes into both of these, actually, so I can divide that one and leave a 5, and that one leave a 1. So overall, I'm just going to rewrite that as the square root of 5 over 3. And that's that, right? Okay, so here's the first question where we get a few variables to throw in the mix. So I'm still going to highlight these guys up like that. 3 and 12, like so. And we're going to ignore the cube root for now, or we're going to ignore the index. We're going to write it, but we're just not going to really consider the consequences of it right now. We're just going to simplify this fraction. So I've got this negative here, and 3 and 12, well, they can both be divided by 3. So I'll divide that one by 3 and this one by 3. It's going to leave me with 1 on the top and 12 divided by into 3 parts. Well, there'll be 4 components of each of those parts. All right, and then we've got a cube root on the top and a cube root on the bottom. Now, what can I divide these guys by? Well, 64 and 8 means I can divide them both by 8, but I can see they both have x's in them too, so I can at least divide them all by an x. And when I do that, on the bottom I just really get a cube root of 1 again. But here I get, when I divide 64x raised to an exponent of 4 by 8x to the power 1, well, 64 divided by 8 is 8, and x raised to a power 4 divided by x raised to a power 1, we subtract those exponents. So we're going to 8x cubed. Okay. So I'm going to get rid of those ones here, because cube root of 1 is 1, and that's 1. So it's going to give me the cube root of 8x cubed negative over 4. That's all well and good. Now I might ask myself, can I resolve the cube root of 8x cubed? What times itself gives me 8x cubed? What times itself gives me 8x cubed? And I might just check, is there a number? And I think there is, actually, because I know 2 times 2 times 2 gives me 8, right? It's a perfect cube. And x times x times x is going to give me x cubed. So that whole top can really be rewritten as, well, the whole fraction is negative, and that whole thing, instead of cube root of 8x cubed, I'm really just going to write 2x, and on the bottom 4, and then say, well, I can simplify that fraction by dividing the top by 2 and the bottom by 2, and I get negative x over 2. Okay. Now, you might just double check, be careful here, that in question K, this 5 is not the index, it's a power of n. I'm going to just zoom in there so you can really see that. There we go. And we'll just refocus that. And that's the same with the cube here. That's actually just a power of n. Okay. So we'll again think of these separately. We'll look at the indexes by themselves, the radicands by themselves, and the coefficients, n raised to the power 5, n raised to the power 3, by themselves as well. All right. So what are we going to get here? We're going to divide. I can see that I can divide those guys. So n to the power of 5 divided by n to the power of 3. That's going to give us n squared. And I'll have a square root on the top and a square root on the bottom. And, okay, it looks like I can divide 36 and 9. I can divide them both by 9. And the question is, what power of m can I divide both of these by? And the rule here is that you always want to take the highest power of the variable that you can. You can divide them both by m to the power 5. So when you do that on the top, 36 divided by 9, you get 4. And m raised to a power 7 divided by m to the power 5, we subtract those exponents. So it's going to be m to the power of 7 take away 5, which is m squared. And on the bottom, well, we're just dividing something by itself, so that's going to give us a square root of 1. Now, both of these square roots can again be resolved. So it's going to give us n squared and times 2m, because 2m times 2m is 4m squared over 1, and I'm not going to write the 1 because I would have to write it again and again, everything under 1 over 1. Now, typically, this isn't really how we consider the final form. We always like to write the constants, like 2, in the front as a coefficient. And I also like to write them in alphabetical order, if I have multiple variables. And that is just some formatting that doesn't make my answer any more right than yours if you wrote it like that. It just means it will match what is typically written in the answer key of math textbooks more. And getting in the habit of writing answers in that way makes it a lot easier for you to check your answers later. It's less confusing. Okay, so this question looks a little hairy. So looks like there's no coefficient business that we're going to be able to deal with. So I'm going to write the things that are going to remain to start with. So I'm going to write the cube root. And looks like that 2e is not going to do anything. And I'm going to write my cube root over here so I don't get that confused with the power of 3 on the e. And the question is, okay, well, what multiplies, or pardon me, divides into negative 32 times e to the power of 1008 over 4 times e to the power of 1005. Well, I can divide them both by 4, and I can divide them both by the highest power, pardon me, by the lowest power of e that I can see. So I'm going to divide them both by e to the power of 1005. That's kind of similar to what we did here. It's just the extreme case, right? Nothing really that different about what we're doing here and what we're doing here. It just kind of looks more confusing. And we have to be bold and say, well, it's not sufficient for something to look more confusing. It actually has to be more confusing before we're going to get intimidated. So, what are we going to get when we divide negative 32 by 4? Well, it's going to be a negative number. And 32 is in the 4 times tables. It's 8 fours. 8. And e to the power of 1008 divided by e to the power of 1005. Well, there's a difference of 3, right? We're subtracting them. So we're going to e raised to the power 3. And on the bottom, it's just a cube root of 1 because we're dividing something by itself. What you might have noticed is a bit of a pattern with this practice sheet. Okay, so what are we going to get here? Well, it looks like we have a cube root that can be resolved. What times itself times itself is going to give us negative 8e cubed. Well, negative 8 is one of our perfect cubes. It's negative 2 times negative 2 times negative 2. And to get e cubed, we need 3 e's because we add the exponents, right? Okay, so that tells us that the whole top can be rewritten. So I've got negative over negative 2e. Now on the bottom I've got 2e. And I'm going to multiply that by the cube root of 1, which is 1. I'm not going to even write that I'm multiplying it by 1. Okay, so what's happening here? So it looks like these 2e's, I have a 2e on the top and a 2e on the bottom. So we're going to cancel those guys out, leaving 1 on the top and 1 on the bottom. And we also have 2 negatives, which cancel out to give us positive. So actually you're going to end up with positive 1 over 1, which is 1. So the whole thing actually simplifies to 1. And I think here is where you could definitely agree that this is more simple than this form. All right. So we'll look at a couple examples where we have 2 terms on the top. And so what we're going to do is, as long as you have a common factor with all 3 terms, you can divide the top by, well, in this case, 3 goes into all 3, right? So I'm going to divide the top by 3 and the bottom by 3. And I really mean root 3, right? So I'm going to get root 4 minus root 2 over root 3 divided by root 3. That's going to be root 1. And, of course, root 4 and root 1 are both perfect squares. I can write that as 2 minus root 2 over 1, which is actually just 2 minus root 2, right? Okay. Now with this question, let's not forget radicals with radicals and coefficients with coefficients. So I can see I can divide, I have actually the same 3 numbers I used here, 12, 6, and 3. So they all can be divided by 3. And I'll leave it with 2, 4, 1. And for the inside of the radicals, the radicands, looks like they can all be divided by 2. So that's going to leave me with, I'm going to write my 2 here, plus my radical, 4 radical over 1 and my radical. And then inside here, I'm going to divide it by 2 and get 12. I'm going to divide 8 by 2 and get 4, and divide by 2 by 2 and get 1. Okay, so I get 2 root 12 plus 4 times root 2 is actually 2. Pardon me, root 4 actually resolves to 2. And 1 root 1 is just 1, so I'm not actually going to write it. Now, that's great. Now notice 12 has a common factor. Pardon me, has a factor that is a perfect square. 4 is going to go into 12. So I can actually rewrite 2 root 12 as 2 root 4 times root 3 plus 4 times 2, which is actually just 8. And that root 4 again becomes a 2, so it's 2 times root 3 plus 8, which is 4 root 3 plus 8. There we go. Again, let's just make sure we are only focusing on radicands with the radicands. And looks like there's no coefficient on the bottom, but I'm going to highlight these coefficients just so I don't get confused. It's negative 6, I guess. All right. So it looks like all we can really do here is we can divide each of these guys by 2. That's going to give me 1, that's going to give me 9, and that's going to give me 10. So I'm going to get 8 root 10, take away 6 root 9, all over root 1, which is just 1. Okay, now that's fine, except root 9 can be simplified, right? It can become 3. So overall, we get 8 root 10, take away 6 times 3. And lastly, 8 root 10, take away 6 threes is 18. And then we're done. Okay, last question here. So again, we're going to look at the radicands and coefficients there. And I'm going to divide each of those radicands by, looks like, does 6 go into all 3? No, 6 doesn't go into 27. So maybe only 3. So I'll divide them each by 3. Okay, now when I do that, I got to rewrite those coefficients here because they're not going anywhere. 5. Because 5 and 4, first of all, don't have any common factors. But even if they did, you would still need a coefficient in front of the root 27. So we're just going to call that 5 root. And what do we have here? 6 divided by 3 is 2. Take away 27 divided by 3 is 9. And we've got 4, and root 12 divided by 3 is 4. And a couple of these guys can be resolved, right? Root 9 is 3, root 4 is 2. So overall we get 5 root 2 take away 3 over 4 root 4 times 2. And that becomes 5 root 2 take away 3 over 4 times 2, which is 8. Okay. And we'll call it there. Let me know if you guys have any questions about any of that. Drop by during Flex or sometime after school. All right. Good luck studying, guys.